So here so far we have seen how AC circuits behave and how they are analyzed, and we can say that in a way we could simplify the analysis of AC circuit by putting the sources in phasor domain, and similarly putting according to that putting the impedances therein in a complex form, and it becomes very much the analysis becomes very much similar to DC circuits. And we have analyzed and we also saw that all kind of AC circuit, all the theorems, how they are applied, all the methods of analysis, that is mesh and node analysis, how they are applied, and the theorems such as Norton, Thevenin, and maximum power transfer theorem and superposition theorem, all these theorems we could apply in the same manner as we do for DC circuit. If we are able to represent, that was all because we could represent the circuit in a phasor form. Now we'll go further for a very important concept, that is three-phase circuit. And three-phase circuit are in fact important in the sense that throughout the world you find the power transfer or power transmission happening in these kind of circuits, that is three-phase circuits. So three-phase circuits are in fact you can say central theme for power transfer, and we will see how these three-phase circuits are analyzed, how they are simplified for easier analysis, or maybe sometimes for approximate analysis, and for making the correction fastest. Before that, we will see what three-phase circuit actually is, and how three-phase voltages are generated. So if you are able to see this diagram, this is essentially a diagram of a three-phase generator. Okay, if you see this, there is N and S. It is kind of a magnet, which is in fact a electromagnet. Okay, and this can rotate. So this electromagnet rotates. So this is the direction of rotation shown here, and these are the this structure which you see in blue or purple, whatever you call. This structure basically is static. Okay, and in this structure you find there are conductors here, which are essentially the coils which are there, and this magnet is rotated in this structure in this coils, and this rotation of this magnet basically gives you a variation of magnetic fields which induces current in these coils. Okay, so that is what this diagram basically is. You must have seen such diagram or analyzed such diagram in your earlier classes for seeing how the dynamo works. So basically it is showing you a kind of structured way of generating voltages in AC circuit. So let us try to see what this is. If you see this A, this is actually a set of same coil. So in one case, if the current is going in, this is actually rotated from behind, and the same comes over here. So in one case, if the current is going, other case it is coming out of it. So it is the same coil A and A dash. So this is one coil. Similarly, you find this B and B dash. So it is same set of coils, one seen from the two sides. So it is a cylindrical structure. Okay, this machine is a cylindrical structure, and you have A, B, and C coils placed on that, and this magnet is made to rotate by some prime mover. Some kind of mover will be applied so that it can rotate this magnet, which is essentially an electromagnet. And when this rotates, there is a rotating magnetic field produced by this magnet. So this magnetic field is changing over the coils all the time, and these coils basically give rise to EMF. Okay, the EMF are generated in these coils. So these are the three set of so if I draw these three coils like this, so if this is say coil A, and this is A and A dash. Okay, and Same thing I am trying to make it electrically here, not showing how actually it is placed in space, but electrically this is B and B dash. So these are coils, three coils, which see the magnetic field changing across it, and therefore the EMF are generated in it, and they give rise to EMF. And these are basically, these coils act like a voltage sources. So sometimes here they will show these coils as voltage source. So this is a AC voltage source. You know it is a changing magnetic field. So this is A and A dash. So this is one voltage source. And similarly, the same coil can be represented as another voltage source, B and B dash, and C and C dash. So these voltages sources are essentially coils in which EMFs are generated because of changing magnetic fields. Now let us try to see if this changing magnetic fields are there, what kind of EMF are generated in them. Okay, so if I take this particular A here, so whatever is the, if I try to draw the EMF generated in A, so this is what I can say, it is a sinusoidal waveform. So you can see it is generating a a sinusoidal waveform. So this is the waveform it generates. So let us assume that this is the waveform for VA. We know that it is going to be sinusoidal. And similarly, the same condition happens in coil B, but after certain amount of time. So whatever happens with A, coil A and A dash, same thing happens with B and B dash. And but there is a small time gap between them. Okay, so this time gap is being shown, and this time gap is essentially the same in terms of, if I want to write that time gap in terms of angles, it is 120 degrees apart. So this is 120 degree apart. Same thing happens with coil in B. So this is what you have in B, and after 120 degrees again here, that is at 240 degrees or a certain amount of time, same thing happens with C. So these are the three voltages generated, which are separated by an angle of 120 degree, which are placed symmetrically on the what you call, this is a stator part and this is the rotor part. So rotor because it is rotating all the time, and stator is a fixed part. So these are the coils which are placed on the stator. So that is how these three voltages are generated, and these three voltages are in fact separated by 120 degree angle to each other. So that is what is three-phase system. Okay, so by place, now you can ask why this arrangement is to be done. See, we are anyway going to rotate this, so we can place one coils or two coils or three coils, and we try to maximize the number of coils. And this three phase is a kind of good number which does two things. It gives you more number of voltages. You can use the whole periphery properly. You could also generate only a single phase if you wanted. So just have A and A dash and you generate it. Okay, but rest of the places would be empty and you can use that place. So that is what it does. Second thing is, when you place these coils in this way, it also gives the prime mover a constant amount of torque. So when you are rotating it, you don't want that at times when there is EMF generated or the current is flowing in that, at that time you see more torque, opposing torque on this electromagnet. And when there is no EMF produced, that is at this point no EMF, at that time the torque would be, no torque would be, opposing torque would be there. So this torque is not uniform if you have only one coil. But if you place the coils, three coils in this fashion, exactly symmetrical, if you say all A, B, C, three phases are symmetrical to each other, then this particular prime mover will see a constant torque being applied to it. So that is also a thing that you need to have a constant torque. Otherwise it will be, sometimes torques will be maximum, sometimes it will be minimum or zero, or maximum and zero, and that is not considered to be a good machine. Okay, Anyway, so when three phase voltages are like this, so we can write the phase voltages here. Let's say in phase A dash, here it is AN, but let us take it as A and A dash. You can take it as A and A dash. That can be written as Vm cos omega t. So let us take that as a reference. Vm cos omega t is the first sinusoid, which is this. Similarly, VB dash, that is in the second phase, it is actually lagging by 120 degrees. So same thing, same voltage would be generated because it is in same condition, except it is generated 120 degrees apart. So same conditions will be happening after an angle of 120 degrees or equivalent time, whatever you call. And similarly, VCC dash would be same way, but the angle of 240 will be there. So these are the three phases, if you see, and these are the three voltages which are generated. Now when these three sources are there, which are essentially coils in which voltages are generated or EMF are generated, these three coils or these three voltage sources can be joined in different ways. Okay, because one way is you have voltage phase A, phase B, and phase C. That is, you can say this is A dash, B dash, and C dash. So three phases are there, and if you want to transfer this EMF to a large distance, then you have to transfer this one set, the other set, and the third set, and therefore you will require this much conductor for transferring. That is, 6 conductors would be required, but we don't use 6 conductors. We intelligently try to do something with these voltage sources so that the minimum number of conductors are required for transferring this EMF or the powers to the loads. So this is basically generator, and from there we are transferring to the load. Okay, so if you go by this way, that which is very simple and very straightforward, you'll need 6 wires, and that is quite costly. But if you join them, these 3 voltage sources, in such a way that then you need actually only 3 wires for transferring this power. So we'll see how that is done. Just here, if you see, this is basically showing that this Vm we are using in here, and it is basically Vrms time √2. So that we have already seen earlier. Now let us see how they are connected. So if I take these 3 voltage sources, okay, 3 A, B, and C, as we saw there, A dash, B and B dash, C and C dash. What I can do is I can just short out these 3 voltage sources together and use this 3, transfer this 3 to the load. So only 3 wires would be required, and this actually remains here, and that is called Y connected or star connected sources. So my sources get connected in star, and this becomes a reference or a reference point, or you call neutral. Okay, so this is what is drawn here. Same thing drawn in a slightly better fashion to look like Y. But here it is essentially the same condition. So this is all 3 joined together, one end, okay, which is called the neutral end. So all this is basically A dash, B dash, and C dash, these 3 points joined together to form one point N, and then you have 3 phases brought out, and these 3 phases are used to transfer power to a longer distance. So wherever you go, you can connect your connect your loads across these phases. How they will be connected, we will see. There are different ways to connect, but what we find here is, by doing this kind of jugglery or joining these 3 phases together and forming a reference point, allows us to transfer this EMFs and subsequently the power only through 3 wires, and that is a big saving. And second one is, I'm just writing the same, these 3 voltages now, VAN, because VA dash is now N, B dash is now N, and C dash is now N. So I'm writing the same thing in a phasor form. So in phasor form it is now VRMS angle 0. So A, if I take it as a reference, it is VRMS angle 0. Then B is 120 degrees away from it, so minus 120 degree. And then C is, I think, should be minus 240, which is wrongly written here, so you can correct it. It should be minus 240 degrees. So this is same thing represented in phasor form, and the sources are connected in Y form. So this is one way of connecting the sources, which is called Y connected source. Now the same three voltages A dash, B dash, and C dash could also be connected in a delta connected source or a delta connected fashion. Okay, so if you see here, this is A and this another point is A dash. So this A dash and B dash point are connected together, but we are taking this as a reference here, writing the name of only B here. So this is A dash connected to the point like this. So it is, if you see in this diagram, I'll just try to use this one. Sorry, I'll try to use this space then. So if I have this three phases like this, A dash, so if I connect this A and A dash, and I connect this A dash to B. Okay, so now this is B dash, and I connect this B dash to C. Okay, so now I take this out, C, and this C dash again I connect it to A. So this is called star connection, and I can bring out these 3 points for transferring the power. So A, B, and C. Similar way, but now the sources are not connected. The three are not tied together to get a neutral point, but this is called a delta connection, another kind of connection that is called delta connected source. So this is delta connected source. Same thing shown, whatever is shown here is shown in a fanciful way to look like delta. Okay, so again, if I want to give them the naming here, now here it is no more AN. Okay, like here it was a neutral point AN, BN, and CN. Now in this connection you don't have a neutral point anymore, you have A and B, so that is AB. If I take this as a reference, then I take VAB as a reference with angle 0, so this is my angle reference 0, and then I take B and C, so that is VBC, but the magnitude is always the same. The magnitude of, because when you see, the magnitude is going to be same, because only the angle is going to be different, because all three are same kind of coils, and same in a similar fashion. So only angle differs. So the magnitude is VAB, but angle is minus 120, and similarly VCA, that is this one, that is voltage between A and C, that is basically this and this point is VAB, again magnitude here, and minus angle 240. So these are what you call different ways of connecting the sources in a generator, so that can be brought out, and with least number of conductors we can transfer this EMF. Okay, so I'll stop here for a while. I'll stop here, and then for this, so that this is a smaller video. Thank you for now.